Welcome to lab number 2 of the Biomedical Engineering 2100 class. For today's lab, we're going to investigate Darcy's law and some aspects of filtering. But before we start, I promised you last week that I would talk about some of the answers to the problems at the end of the lab from last week, namely what happens to the standard deviation and the mean of our values of our measurements if we had many measurements. Now, we only took 5 measurements of mass density in the lab last week, and that's really not enough to get good statistics. So to answer the questions on the worksheet, we've collected data from 2 years ago over the course of several lab sessions where the students were doing the very same measurements that we did, but they've collected almost 300 data points here. And this is the raw data. Notice it's somewhat scattered. What we're interested in today is how the standard deviation varies as you accumulate more and more samples all the way up to the 300. Well, notice that after the initial drop, which is to be expected as we gather a few samples to make it more steady, sometimes it rises, sometimes it falls. Sometimes it rises and then falls. It rises when people get a little bit more sloppy and there's more deviation in their measurements. And it falls when people get a little bit more careful about how they're doing the experiment. So the answer to the question is sometimes it rises, sometimes it falls, depends upon the care taken when doing the experiment. But notice that it never goes to 0. It would only go to 0 if the experiment could be done exactly precisely with absolutely no error. And that's not humanly possible. Now let's look at the mean. Here is the mean as you accumulate more and more samples. It varied quite a bit at the beginning because there weren't very many samples. But as you gathered more and more samples, notice that the mean gets a little bit more steady, a little bit more reliable. So the answer to that question is the more samples you have, yes, the more reliable, the more steady, the less fluctuation there is in the mean. Now, we didn't do this, but you'll do this in a statistics class, and that is you can find the standard deviation of the mean itself. And the standard deviation of the mean itself is a measure of the standard error of the mean, or SEM. And here's how the standard error of our measurements fell. Notice that it drops quite a bit at first, and then it sort of levels out. In fact, you'll learn in statistics that the curve of the standard error of the mean follows, if they're independent measurements, 1 over the square root of n. So you get quite a bit of an improvement in the reliability of the mean at first, but then it sort of flattens out, and there's a law of diminishing returns. Because of this square root, notice that if you had 16 samples, in order to improve your standard error of the mean by a factor of 2, you'd have to go all the way out to 64 samples. So there is a law of diminishing returns here. So as you've read about in chapter 2, Darcy's law came about because Henry Darcy, who was a French hydraulic engineer, was measuring the flow of water through tubes filled with sand in Dijon, France, in the middle of the 18th century. Well, we don't want to go to the trouble of measuring water through sand in tubes. So today what we're going to do is we're going to measure the flow through a porous membrane, namely filter paper, that's placed inside this funnel called a Buchner funnel. And then we're going to look at how much water goes through that filter paper when we apply a negative pressure from this vacuum pump on the outlet. We'll use a stopwatch to measure the volumetric flow rate Q. Before we get started with our experiments, though, let's see how this relates to some figures in chapter 2. So here's figure 2.3 from the textbook, showing the general arrangement for the flow through a porous membrane, flow rate Q, caused by a pressure drop P1 at the inlet minus P2 at the outlet. The thickness of the membrane is H, and the area of the membrane is capital A. How does that relate to today's lab? Well, in today's lab, the flow is vertical from top to bottom. So I'm going to turn this figure, still applies, more in the orientation of today's lab. And then I'm going to show you a sketch of what today's lab looks like. Same variables, but in today's lab, the flow is vertical from top to bottom, flow rate Q, caused by a pressure drop P1 at the inlet, which is just atmospheric pressure because we're not putting a positive pressure on the inlet. We're actually putting a negative pressure on the outlet. So the outlet pressure is P2, which is atmospheric pressure, which is everywhere, minus the pressure caused by the vacuum pump. Now to find the pressure drop, which is defined as P1 minus P2, you put in those values and notice that the atmospheres cancel out. And we're just left with the fact that the pressure drop across the membrane is the vacuum pressure. Notice that the membrane, the filter paper, has a thickness H and an effective area, capital A. Before we can apply Darcy's law to today's lab, we need to make some measurements of the physical properties of today's system. Starting first with the thickness of the filter paper. That's the edge thickness of the filter paper. I will use a micrometer to find that thickness, and I measure it to be 0.43 millimeters. 0.43 millimeters. Please mark that down on the appropriate spot on the worksheet for today's lab. The next measurement we need is the diameter of the filter paper. I'm going to measure that with this ruler in centimeters, and it's exactly 9.0 centimeters. 9.0 centimeters. Mark that down at the appropriate spot on the worksheet. The next thing we might need is the outlet length of the funnel, called a Buchner funnel. And I'm going to measure that in centimeters also. And that is 7.5 centimeters. 7.5 centimeters. Please write that down. Notice that the Buchner filter has a number of holes here. If we count the number of holes there, we find out there are 91 holes in the bottom of the Buchner filter. Write that down. And then the diameter of each hole, well, it's hard to measure with a ruler because you can't get a ruler in there. So what I'm going to do is use a trick. I'm going to use these drill bits here, and I'm going to take the drill bit that has the closest diameter to the hole, which I can see here is 5/64 of an inch. 5/64 of an inch. Notice that those are imperial, or English units. And using the blunt end of that drill, I can show that that's just really close to the diameter of each of those holes. So that's a real tricky way of finding the diameter of those holes. 5/64 of an inch. Please put that down on the worksheet. And then finally, we may or may not need this, we need to know the maximum volume in the funnel, at the top of the funnel, how much volume that will hold. And I've measured that earlier as 350 milliliters. Write that down in the space provided. Now, let's obtain some experimental data. For the first measurement, you'll see from the worksheet, we're going to determine the flow rate Q1 through the filter paper for a pressure difference of 100 millimeters of mercury. I have the filter paper in the funnel, and I pour water on top, enough water to filter through. And then, as I apply a vacuum of 100 millimeters of mercury, which is right here, I will use a stopwatch to determine how much time it takes to filter 100 milliliters of water through the filter paper. Starting right now. I'll keep the vacuum at 100 millimeters mercury and watch to see how long it takes to collect 100 milliliters of water. We're getting there. Looking at the markings on the beaker, on the collection beaker. Right now, 38.2 seconds. 38.2 seconds for 100 milliliters of water. Please put those numbers down, and then it's easy to calculate Q1 in units of liters per second. Now let's do the measurements necessary to find flow rate Q2 for our pressure difference of 200 millimeters of mercury. I've emptied out the bottom flask here, filled this with water, and now I'm going to use the stopwatch to determine how long it takes to filter 100 milliliters of water through at a higher pressure difference, namely 200 millimeters of mercury. Starting right now, keeping the pressure at 200 millimeters of mercury. It's filling faster this time, of course. Getting there. Getting there. Right now. That is 26.4 seconds. 26.4 seconds. Please write that down in the appropriate spot, along with a volume of 100 milliliters on the worksheet. And that will allow you to calculate Q2 in liters per second. And then the next thing we're going to do is we're going to plot both of those points, along with a third point, on the graph, following good graphing practices. Now that we have two data points, Q1 and Q2, let's plot them as a function of their driving pressure. In this section of the worksheet here, we'll plot it by hand. Since we're going to be doing a lot of plots this semester, many of them by MATLAB, for all of them, I'd like you to follow good graphing practices, such as titling every graph with an appropriate title. Here's the location for today's graph. Write in some title that you think is appropriate. And then we're going to label the variables along each axis along with units, appropriate units. Now notice that the two variables have already been labeled on this graph, but we don't yet have their units. You should put those in. And then we should label each axis tick increment with a number, including the origin. What I mean by that is that every tick mark along each of the two axes should have a number associated with it, and then label the origin with a 0 and a 0 to show where the origin is. And then for each of our data points, we're going to mark them with a distinctive marker like an X or a star, not a dot. And we'll have two, actually three, data points. Q1 will go in this region somewhere in here. Mark it with an appropriate marker. And Q2 will go somewhere in here. Mark it with an appropriate marker, such as an X or a star, not a dot. I'll tell you why in a second. And then notice that the origin also can be considered a third data point, because we know that if we have 0 pressure, we'll have 0 flow. So that becomes our third data point. Put a marker on it. And then draw a straight line between the points that doesn't hide the markers. We're going to draw a straight line between those 3 points. And if it were a dot, that line might hide the marker, the dot. And so we wouldn't know where the data point is. That's why we don't use dots for markers. And of course, be neat in everything you do today. Now that we have our plot done, let's go down to this discussion. We want to compare that plot to figure 2.4 in the textbook to tell whether the filter paper is deformable or not. Here's figure 2.4. For an ideal membrane, notice that the higher the pressure, the higher the flow Q in a linear fashion here. If the membrane is deformable, though, you're going to have a curve that looks something like this, because the higher pressure is going to squeeze off some of the pores in the membrane, and you're going to get less flow through for a given pressure. Does our filter paper follow a straight line, or does it follow more a deformable shape? Now, we only have 3 data points, but I think you'll be able to answer that. If it is deformable, you should give a possible reason why you think that the cellulose filter paper might be deformable. Now let's turn to worksheet number 2. This is where you're going to do a calculation of the permeability of the filter paper, and you're going to have to do a lot of units conversions here. So using the value of Q1 and its associated pressure and all of the physical parameters that we measured at the beginning of the lab, along with the viscosity of water from the appendix, which I'll show you in just a minute, find the permeability K from equation 2.3, first in units of meters squared. That means you're going to have to convert everything to the SI system. And then once you get that, convert that back to centimeters squared, and report your answer with an appropriate number of significant figures. We'll let you decide how many you want to use. Now, where do we find the viscosity of water? It's in the appendix of the textbook. Here's water at 20 degrees C. We can assume we're roughly at that temperature. And notice that it's 1 centipoise. 1 centipoise. Now, poise is not an SI unit. It actually honors poisson that you'll learn about in lab number 3 in chapter 3. But you can convert it to SI units with this conversion factor right here. We'll let you do that. And then the equation that you're going to use, equation 2.3, is Darcy's law, and that is in the textbook here, 2.3. And what you're going to do is, you know Q, you know viscosity, you know thickness, you know pressure difference, you know area. You're going to turn this equation around and solve for K. I'll let you do that now, because after you get your value, we're going to do a reality check. And the reality check is you're going to compare your value that you just determined today from a value of another filter paper, cellulose filter paper, that's also found in the appendix. You're going to compare those 2 values. Let me show you where the value of K for the other filter paper is. It's again in the appendix B. It's the cellulose filter paper, which is a bit different than the one we've used, and here's its value of permeability. Now, when you get your value of K, compare it to that value that we just looked at. Today's filter paper should be 2 to 3 times faster than the one listed in the appendix. So check your K to see if that represents a filter paper that's 2 to 3 times faster than the one in the appendix. If it's not, you've probably made a mistake of one of 2 kinds. Either you've made a units conversion mistake, so check all of those, or maybe you have calculated the area incorrectly. So if that's true, let's stop right now and check the reality check on your answer. And if you have a problem with the reality check, stop the video and I'll come back and see if we can help you. Okay, we're back. I assume that you've calculated now the permeability of the filter paper and compared it to the value in the appendix, and that you've passed the reality check. If you have, great, you can go on. If you haven't passed the reality check, it could be that you've done a units conversion incorrectly, or perhaps you've calculated the area A of the filter paper incorrectly. And this is a bit tricky. It turns out that the effective area of the filter paper is not its entire diameter, and its area is not given by pi d squared over 4, but rather the area is only the effective area where the water goes through the filter paper. And since we used this Buchner funnel, It's a very clever funnel that has holes in it. Notice that the filter paper sucks down on the surface of the filter, and the water only goes through where there are holes. That's a really ingenious invention. That's why it has his name associated with it. Because notice that since it's sucked down on the smooth surface and the water only goes through the holes, you don't need any O-ring to clamp around the edges to prevent water from sneaking around through the edges. In fact, here's a demonstration of that. In this particular paper, the people filtered bog water, very dirty water, through the funnel, and notice that the dirty bog water only deposited in the filter where it went through, in other words, only in the holes. Well, we know how many holes we have, we've counted them, we know what the diameter of each hole is, so we can add those all up, and that is going to give us the effective area of the entire filter. Ignore this right-hand side. Use that area. And when you do that, you should pass the reality check. If you haven't, stop the video right now and come back when you've passed the reality check. Well, assuming you've passed the reality check, let's go on and finish up by doing some more filtering. I'm going to try to filter a couple of other fluids, cranberry juice and orange juice, through that filter paper to see what happens. But follow and observe the following video. Now, to finish up, let's try some further filtering of some different fluids other than water. First, I'm going to try to filter cranberry juice. What do you think is going to be the result down here in the collection flask when I filter cranberry juice? Think about that for a second. Is it going to become lighter? Is it going to get through it all? Well, let's try that. Pour some cranberry juice in and start filtering. Now, as you can see, it's coming through pretty much without any change at all. No color change. Comes through about as fast as water. Put down a reason why you think that that might be the case of our observation here. Next, let's try filtering some orange juice and see what happens. I want to point out on the bottle of orange juice it says here pulp free, free of any pulp. So when I pour this in, what do you think is going to happen when the orange juice filters through the filter? Is it going to change color? Is it going to come through at all? Let's try it. Watch what happens when I put a heavy vacuum, quite a heavy vacuum. We're up to almost 400 millimeters mercury. And as you can see, nothing is coming through. Nothing. Can you explain that? Oh, there's a drop of cranberry juice left over, trapped in the filter. But no orange juice is coming through. See if you can figure out a reason why that happens. Put that down on your worksheet. And that concludes lab number 2. I look forward to seeing you for lab number 3 next week.